Okay, we're going to look at this first part of the story with impulses and the nervous system. How do we actually detect the initial stimulus, and how does it get to our brain? So the objectives for this, explain how a stimulus such as pressure on the skin is detected by the brain. How does the information from us touching a sharp object, which we didn't see, how does that information get sent to us, to our brain? So we need to explain how we detect big but not small stimuli. So why is it we will feel a pin, but you don't really feel the clothes on your back rubbing against your skin? You don't. Certain stimuli don't seem to be detected, whilst others are. Also, we're going to look at the order of events that lead to an impulse. So a lot of things you do in the biology course is you've got to be able to go through the logical sequence of events to explain what's going on. And to do that, some of the words we'll go through are potential difference, voltage, resting potential, generator potential. We're going to look at one particular ion called the sodium ion. We've got to talk about threshold level, receptor, and one of the receptors we can talk about is the Pacinian corpuscle. You could also apply this to the light receptors in the retina as well, so I'll talk about them as well actually. Okay, so in order for you to be able to, for information to go from places like your fingertips to your brain, we have to have a potential difference set up. So if we start at the very beginning, this is, imagine this region here where it says receptor, this is your fingertip. The receptor has managed to set up a potential difference. And what I mean by that is, because if you remember from physics GCSE, potential difference is basically voltage. There is a difference in charge between the outside and the inside. And that potential difference is making the inside relative to the outside about minus 70 millivolts. So although, and we call that a resting potential, which gives the impression that it's resting, but actually that requires energy to do that, which we'll go into more detail later on in the next video. So a resting potential has been set up. The inside relative to the outside is minus 70 millivolts. Sometimes it's written as minus 60, whatever, minus 60, minus 70 millivolts, that's fine. And that's been set up because sodium ions, which have a charge of plus, have been pumped outside. And again, more detail will follow on this in the next video. So lots of sodium ions have been pumped out, and now we've got this potential difference of it being positive on the outside and negative on the inside, and it's around minus 70 millivolts, the potential difference. So what happens then if your skin makes contact with an object? We call that stimulus. Like a touch would be one of the senses. So what happens is, as you make contact with an object, this receptor begins to become more permeable, and it's becoming more permeable to sodium ions, and those sodium ions are going to begin to leak in. So they start to bring their positive charge in. And if enough sodium ions leak in, well, what's going to happen to the charge here? It's going to begin to become less negative. So it's going to move from minus 70 to minus 65 to minus 60 to minus 55. And if it gets to minus 55, this is a really important moment, because this is called the threshold level. And that threshold level is important because at minus 55 millivolts, this little protein here, we call this a voltage gated sodium ion channel. It can open up, and it is going to allow more sodiums to enter. And this process is going to continue on and on and on until it gets to your brain. And that's how you're detecting these changes. So this is only going to happen if enough sodium ions diffuse in the first place. And the only way you're going to get enough sodium ions to diffuse in is if this membrane becomes permeable enough. And the thing that's going to dictate how permeable this membrane will be is by how big the initial stimulus is. So this applies also to the light receptors in the retina. The more light that enters your eye, the more permeable the membranes of the receptors become, and therefore more sodium ions can diffuse in. And if enough diffuse in, then we're going to get this change in voltage to this threshold level. If it goes beyond this minus 55 millivolts, then the other voltage gated sodium ion channels can start opening. Let's just write this. So voltage gated sodium ion channels. So that's really important. So this idea of there being a big enough change in voltage, we're talking about this term here, generator potential. All right. So if the generator potential isn't big enough, this sodium ion channel, the voltage gated one, isn't going to open. So if the generator potential isn't big enough, then the threshold level is not going to be exceeded, and therefore this opening of the voltage gated channels isn't going to take place. So it's really important for you to detect any changes in the environment around you. It has to have been big enough to have initially caused these sodium ions to be able to diffuse in the first place. Okay, so yeah, so that'll do for now. Let's just double check one thing. Describe the order of events. We've gone through that. So let's just quickly just do this one more time. Describe the order of events that lead to an impulse. So stimulus causes receptor membrane to become more permeable to sodium ions. Sodium ions diffusing. If enough sodium ions diffuse in, threshold level is exceeded. And if threshold level is exceeded, the voltage gated sodium ion channels will open. And that will continue all the way to your central nervous system, to your brain. And therefore, you'll be able to have detected those changes. If the stimulus is not big enough, the membranes will not become permeable enough. Therefore, not enough sodium ions will enter, and therefore threshold level will not be reached, and the impulse is not going to make it to the brain.